In this video segment, we'll talk about how the resting membrane potential of neurons is generated. And as a starting point, we have to discuss the ion gradients that are found across the neuron membrane. In a typical cell, we have a high concentration of sodium in extracellular space, in this case 117 millimolar, and a lower concentration of sodium inside the cell. The gradient for potassium is just the opposite. There's a low concentration of potassium outside and a high concentration of potassium inside the cell in the cytoplasm. The chloride concentration is high outside and low inside, and the imbalance of positive and negative charges is compensated for by having a high concentration of organic anions, negatively charged ions, inside the cell. Now, these ion gradients are established and maintained primarily by the action of the sodium-potassium ATPase, and with the hydrolysis of one molecule of ATP, 3 sodiums are pumped out of the cell and 2 potassiums are pumped into the cell. This establishes the sodium gradient and potassium gradient, and then the sodium gradient in turn is used to establish other gradients such as the chloride gradient and the calcium gradient across the cell membrane. So, given these initial ion gradients, how is the resting membrane potential generated? Well, first one has to understand what the electrochemical equilibrium potential is. And we'll talk first about the electrochemical equilibrium potential for the potassium ion. And we'll use this drawing here as an example. Let's assume that we start with a cell that is permeable only to potassium. The cell has ion channels shown here and here that are permeable to potassium. For this argument, we're going to assume that these potassium channels are actually voltage independent. They're always open. They're not gated by voltage, but they're always open, so we can think of these as leakage potassium channels. And we're going to start with an initial condition where the voltage inside the cell is 0 compared to outside the cell. And we have a high concentration of potassium inside and a low concentration of potassium outside the cell. This potassium gradient is established by the sodium-potassium ATPase, as we've already discussed. Okay, so given these initial conditions, what's going to happen? Well, the first thing that will happen is that there'll be an efflux of potassium outside of the cell because there's a high concentration of potassium in and a low concentration of potassium outside. So this chemical gradient will cause potassium to flow out of the cell. As potassium flows out of the cell, we're moving positively charged ions from the inside to the outside, so that will leave the inside of the cell more negative. And as more potassium ions continue to flow out of the cell, the inside of the cell will become more and more negative. Now, you might imagine that this will continue until the chemical gradient is equal and that the concentration of potassium inside will equal the concentration outside. But in fact, this doesn't happen because as we establish a negative membrane potential inside, this will serve as a driving force for potassium to flow into the cell due to the electrical gradient. Potassium is a positively charged ion. If the inside of the cell is negative, this will cause potassium influx. So now we have potassium going out due to the chemical gradient and potassium flowing in due to the electrical gradient. And as more potassium flows out and as the inside becomes more and more negative, there will be a larger influx of potassium due to the electrical gradient, and then we will reach a voltage inside the cell where the influx of potassium due to the electrical gradient will just equal the efflux of potassium due to the chemical gradient. And at that point, we are at an equilibrium. The same number of potassium ions is moving out per unit time as is moving in due to the electrical gradient. So we have a equilibrium condition where there's no more net potassium flux across the membrane, and this will happen at a particular voltage, negative voltage inside the cell. And the value of this voltage is called the electrochemical equilibrium potential. And as you can imagine, the larger the original potassium gradient, the more negative will be the electrochemical ion potential, equilibrium potential. It would be useful if we had an equation that could tell us what the equilibrium potential for an ion is based on the chemical gradient of that ion across the cell membrane. And indeed, such an equation exists. It's called the Nernst equation, and I'd like to take you through an abbreviated derivation of the Nernst equation. And what we will be doing is coming up with expressions that tell us how much work is needed to move a mole of ions against its chemical gradient and its electrical gradient. So we start with looking at the chemical gradient, and we find that the work needed equals RT times the natural log of the ion concentration outside over the ion concentration inside. In this equation, R is the universal gas constant, and T is the absolute temperature in degrees Kelvin. We can come up with a similar expression for the amount of work needed to move a mole of ions against its electrical gradient, and that expression tells us that the work equals V times Z times F, where V is the voltage difference across the membrane potential. F is the Faraday constant, which tells us how many coulombs of charge there is a mole in a mole of ions. It's kind of a fudge factor. And Z is the valence of the ion. And of course, for potassium, the valence is +1. Same for sodium. Calcium has a valence of +2, and chloride has a valence of -1. When we are at equilibrium and the flux due to the chemical gradient equals the flux due to the electrical gradient, then the work needed to move against these two gradients should also be equal, and so we can set the two expressions we derived in the previous slide equal to each other, and that's shown in the top equation. We can then solve for V, the equilibrium potential, and we find that V equals RT over ZF times the natural log of the ion concentration out over the ion concentration inside. Now RT and F are all constants. T is a constant if we assume that the temperature doesn't change, and if we substitute the values for these parameters, we find that RT over F equals 26 millivolts. So we can substitute this back into the equation, and we find that the equilibrium potential equals 26 over Z, the valence, times the natural log of the concentration gradient. Now it's useful to express this equation in log base 10 instead of natural log, and we can substitute log base 10 by simply changing the 26 millivolts to 58 millivolts. And we find that the equilibrium potential in millivolts equals 58 over Z, the valence, times the log of the ion concentration out over the ion concentration in. This is the final form of the Nernst equation that we'll be using, and it states once again that at equilibrium, the membrane potential of a neuron will be 58 millivolts divided by the valence times the log base 10 of the ion concentration outside over the ion concentration inside. And I think you can see that this equation makes intuitive sense, and let's just run through a few examples to illustrate this. If we use the example of a cell that's permeable solely to potassium, and we assume that the potassium concentration inside is 10 times the concentration outside, let's assume, for instance, that the potassium concentration inside is 100 millimolar and outside is 10 millimolar, then to solve the equation, the log of 10 over 100, log of 1/10 equals -1, and we're left with a voltage of minus 58 millivolts. Z, of course, the valence of potassium is +1. If we look at a cell that's permeable solely to sodium in contrast, and let's assume that we have a sodium ion concentration gradient where sodium is 100 millimolar outside and 10 millimolar inside, then the log of 100 over 10, the log of 10 equals +1, and we're left with a equilibrium potential of +58 millivolts. Now there are a few important things to remember about the equilibrium potential of a neuron. First, since there's no net flux of an ion across the plasma membrane, no energy is needed to maintain the membrane potential. So if you have a cell that's permeable only to one ion, after it achieves its equilibrium, no energy is needed to maintain that voltage. Secondly, the number of ions that had to flow across the membrane to achieve the equilibrium potential is very small. If you start at 0 voltage, let's say for a potassium permeable cell, and potassium flows out, very few potassiums had to flow out in order to reach the equilibrium potential. Thus, the initial ion concentration gradient is almost unchanged. There's very little change in the gradient. We'll be closing this video segment with a second in-class exercise. We've just considered what the membrane potential of a neuron would be if it's permeable to a single ion species. What I'd like you to consider for this exercise is what the membrane potential of a neuron would be if it's permeable to more than one ion species. And specifically, we'll be considering the case where a neuron is permeable to both potassium and to sodium. On the graph, we see the voltage, which will be plotted as a function of time, and indicated is the potassium equilibrium potential here, EK, and the sodium equilibrium potential up here. And what I'd like you to consider is what the membrane potential would be if the permeability ratio of potassium to sodium were 10 to 0, 0 to 10, equal at 10 to 10, or if the permeability ratio were 10 potassiums to a single sodium.